order maybe. All right, so SO2Cl2 decomposes into SO2 and Cl2. Okay, this is way choppier than it's supposed to be, but we'll just try continuing it. Do you see a very important phrase in the first sentence of the question? It says, is first order in SO2Cl2, right? This is question 37 on that worksheet. So it says it's first order in SO2Cl2. So based on that, we could do a whole bunch of things right now. Knowing its first order, we could write the differential rate law. Rate equals K times the concentration of SO2Cl2. We know the integrated rate law from yesterday's notes involving natural logarithms, right? We know the half-life equation from yesterday as well. The question says, at 600 Kelvin, the half-life is 2.3 times 10 to the 5 seconds. So T1/2 is 2.3 times 10 to the 5 seconds, a half-life at 600 Kelvin. What is the rate constant? What is the rate constant at this temperature? How am I going to do that? Okay. We remember from our notes yesterday, flip to there. Do we have an equation that talks about half-life and rate constants for first order?
Yes, we do.
In fact, first order half-life is equal to 0.693 divided by K. And do you remember where that magic 0.693 came from?
The natural law.
It was the natural log of 2, right? So this is a very easy question. K then is going to equal 0.693 divided by T1/2. Okay, substitute your number there and get me a value for the rate constant. 0.693 divided by 2.3 times 10 to the 5. Put the units in. Seconds. The numerator, the natural log of 2, has no units. Okay, so there's only seconds in the denominator, which means that the first order rate constants, units, will be time to the -1 in general, and in this question, per second. Okay, whenever you see a first order process, you know that its rate constant will have time to the -1 as its rate constant units. You're dividing by a really big number, so your answer is going to be very small, right? So don't be surprised by that. What do you get as an answer?
1 times 10.
Sorry?
2.01 times 10.
2.01 did you say? 3.01 times 10 to the
-6.
-6. That's a horrible slide. This is, one or two people are away today, and I said I would try to record today's lesson for them. All right, so there is the first, so part B says to us that at 320 degrees Celsius, the rate constant is larger or smaller?
Larger.
2.2 times 10 to the -5. What is the half-life at this temperature? Okay. 320 degrees Celsius converted to Kelvin would be what? 320 degrees Celsius is what? 593 Kelvin. You add 273, right? So this is a slightly lower temperature. It's a little bit surprising that the rate constant is larger. Okay, at a slightly lower temperature, you would normally expect the rate constant to be a little bit higher, a little bit larger. Sorry, at a lower temperature, it should be a little bit smaller. Go ahead and calculate the half-life then. T1/2 is 0.693 over K. Just put in your new rate constant. Put in your new rate constant and find the half-life. Okay, so this question on a scale of 1 to 10 of difficulty is pretty easy, but you had to recognize in the question that phrase first order process, first order kinetics, and then you had to know this equation for half-life, didn't you? Okay? So 0.693 divided by 2.2 times 10 to the minus 5 per seconds, which means that the units for half-life will be seconds, right? Andrew, what'd you get? 31,500. Okay. If you were worried about significant digits, you'd say 3.2 or 3.1, depending on whether that was rounded off, times 10 to the 4 seconds, right? There are only two sig figs in the rate constant. Any questions about that? Christina? The temperature wasn't part of the problem. It's simply the idea that at a different temperature there will be a different rate constant. Okay? Rate constants are temperature dependent. So if you change the temperature, you're going to change the rate constant. Okay? It wasn't part of the problem. Question number 38. Is that worth doing? Is that worth doing, or does that look easy? Let's take a look. Molecular iodine dissociates into iodine atoms with a first order rate constant. So iodine dissociates into iodine atoms. We're told that it's first order. K was equal to, how could I tell just from the constant that it's first order?
Units in seconds.
The units for the rate constant are time to the minus 1, right? So if you see time to the minus 1 as a rate constant, that's a first order rate constant. Part A is very straightforward. We just did that. Calculate the half-life. If it were not first order, would you be using the same equation for half-life? No, it's more complicated, right? Every order has its own half-life equation. So you have to use the correct equation for the given order of the kinetics. So for first order half-life, T1/2 is 0.693 over K. Make sure you're using a lowercase k for the rate constant. In our next unit on equilibrium, we're going to be using uppercase k's to represent equilibrium constants. So don't mix those up. So 0.693 divided by 0.271. Hart, what's the answer here? 2.56 seconds.
Yeah.
Okay, pretty easy, first question. Part B, if you start with 0.050 molarity iodine at the same temperature, how much will remain after 5.12 seconds if we assume that the reverse process does not happen? Assume that the atoms of iodine do not recombine back into iodine. Is that a tough question?
No.
5 point, how long? 5 point? This is a very easy question, isn't it?
Yes.
What makes this question especially easy?
The numbers given.
Back in our grade 9 science, when we looked at radioactive decay, you might have done a question like this then, right? I might have said the half-life for a radioactive decay is 10 seconds. How much will remain after 20 seconds, or 30 seconds, or 40 seconds, right? Would I have asked back in grade 9 how much is left after 17 seconds? The half-life is 10 seconds. Would I have asked how much is left after 17 seconds? No, because back in grade 9, you did not have the integrated first-order rate law. You could only solve problems with half-lives if the time was a multiple of the half-life, right? Is that true here? So we could say 5.12 seconds is 2 times the half-life. The half-life was 2.56 seconds. So it's twice the half-life. And the question is, if you start with 0.050 molarity, how much will be left? You've got 2 half-lives. So after 1 half-life, you'd have 0.025 molarity. That was after 2.56 seconds, right? You with me? We're going 5.12 seconds, so we're going to go another half-life, another 2.56 seconds. So we're going to go down from 0.025 to 0.0125. Okay, with sig figs probably 0.013. Pretty easy. While we're here, let me ask a question that's not on the sheet. Suppose instead of 5.12 seconds, suppose you had 10 seconds. How much of that 0.05 molar, that's what you start with, how much will remain after 10 seconds? What did we know about this process? The half-life was 2.56 seconds. And we also knew that the rate constant was 0.271. How could you answer the question now in grade 11 advanced AP Chemistry when the time I'm giving you is not a nice multiple of the half-life? We go to the integrated rate law. What is the integrated rate law for first order kinetics? The natural log of A at time t equals, come on, look in your notes or say it out loud. What is it? Equals what? Negative kt plus the natural log of A at time 0. Now, an easy way to remember that equation is to remember that for first order kinetics, time and natural log of A is linear and falling, right? That's the test for first order kinetics. We saw that yesterday. So from that graph comes y equals mx plus b, this first order equation, doesn't it? So look at that equation. What are we trying to find in this problem? I want to know what concentration will there be after 10 seconds. So which of the things in this equation am I looking for?
The natural log of A.
No, not the natural log of A. I want to know the A. This is what I'm looking for. Do we know the rate constant, K? Do we know how long it's taking? 10 seconds, right? Do we know, what does A0 mean? The beginning concentration. Do we know that?
Yes.
Well then, let's go to it. The natural log of A will equal negative 0.271 times. Now one thing you have to watch for And I got a bit sloppy here. I should have put in my units. Why? Because sometimes the question will try to trick you by giving you a rate constant in per seconds, but a time in minutes or hours or something, right? Those time units must match the units of the rate constant. Okay, so if you put the units in, you'll catch that kind of mistake. If you were putting per second and then you put minutes, hopefully that would strike you as that's not going to work, right? So 10 seconds plus the natural log of 0.050. Pick up your calculator and evaluate everything on the right-hand side. The natural log of A is equal to what? Negative 0.271 times 10 plus the natural log. Make sure you're using natural log, not the normal log. You get negative 5.706. So I'll keep an extra digit or so. Double check your work. Negative 0.271 times 10 plus the natural log of 0.05 equals. Have we all got that? Mr. Richardson, you got that? You got it. All right, folks, now comes the question of how do I get rid of natural log? If you recall from last year, let's talk about base 10 log for a minute. If I say log base 10 of 1,000, the answer is 3. Because 3 is the exponent that 10 gets raised to give 1,000, right? But notice you can switch from this logarithmic form into an exponential form. You can say that 10 to the power of 3 is 1,000, right? In a natural logarithm, ln, the base is not 10. The base is the number e, right? So we have here, it's not shown, but it's actually a base e. So take this equation and do what we just did at the bottom here. Switch it into exponential form. What will it say? Instead of 10 to the power of 3, it'll say e to the power of negative 5.706. Yeah. Static electricity, it does that. Equals what? Equals A. Equals the concentration of A. Now pick up your calculator. Where will you find e to the power of? It's right above the natural log. So you just go second function ln e to the power of negative 5.706 equals 0.003. And does this answer make sense? Yeah. If you started at 0.05, could you reasonably be down to 0.003? Yeah, that makes sense. And if you thought through a little bit more detail, 2.56, 2.56, 2.56, that's around 4 half-lives, isn't it? Yeah. It's close to 4 half-lives. So half, 4 times, and you're going to get something pretty close to that. Okay? All right. I see someone at the door there waiting for me. Why don't you guys try question number 39, please? Okay, folks, if you are talking, you had better be done. Okay? Not everybody is, Tom. Okay? Question 39, you've now got a first order process again. The rate constant is given again. If we begin with an initial pressure of this, what is the pressure of the substance after 65 seconds. Can we be using pressures in this equation?
Yeah.
Can we be?
Yeah.
Let's make a quick little proof that we can. If you take the ideal gas law, please write this down. Take the ideal gas law. Sebi, you're writing this down. And move the volume to the other side. What do you get? P equals?
NRT.
Let's write it as N over V times RT. But N divided by V, moles divided by volume, is molarity. So let's say that P equals CRT. Now if you take your integrated first order rate law, you don't have to do this every time, I'm just trying to show you why you can use pressures. If you do natural log of A equals negative KT plus natural log of A0, where usually the A and the A0 are thought of as concentrations, right? Notice I've left out the concentration symbols this time. If you move the natural log of A0 to the left, you get the natural log of A minus the natural log of A0 equals negative KT. And what am I going to do with that?
Divide.
This is now using a log rule, the natural log of A over A0 equals negative KT. Look at that way of writing it. Okay? If you have A over A0, and you go back to look at what we've said over here on the side, we can solve for C. C equals P over RT, right? If you take the concentration of A, that's like C in this equation over here, concentration, you could replace that with PA over RT. And you could replace A0 with P0 over RT. Right? And what's going to happen to the RTs in that situation? They'll cancel out. And what will be left is natural log of P over P0. Do you follow that? Victoria, do you understand what I just said? I'm saying that if we take that expression for concentration and substitute it for A and for A0, we're going to get the natural log of P divided by RT divided by P0 divided by RT. The P over RT is A, and the P0 over RT is A0. Do you follow that, Brendan? Now I'm dividing a fraction by a fraction, so you take the reciprocal and multiply, and what's going to happen is that the RTs will cancel, and you're left with natural log of P over P0. So what I've just shown is that the natural log of A over A0 is the same as the natural log of P over P0. So you can substitute pressures for concentrations. It also explains why the units don't matter for pressure. Grade 11 chemistry, gases unit, you can have atmospheres, kilopascals, millimeters mercury. What happens to their units in this fraction? They cancel out. So the units for pressure don't matter either, as long as they are the same, top and bottom. Okay? Brandon?
I don't understand how you went from the natural log of A, natural log of AO, down to the natural log of A divided by A.
Over here we said that concentration is P over RT. So where it says concentration of A, we replace it with P over RT.
Is that like
The one above it, the one above it.
like how you go from like minus to dividing it though?
Yeah.
Like
natural log of A minus natural log of A.
How I went from here to here?
Yes.
Yeah.
Okay, that's a log rule, right? The log rule that said the natural log of a quotient is the difference of the logarithms. That's just a rule from logarithms. And I went backwards with that rule. We had a difference of logarithms, so it's equal to the logarithm of the quotient. Okay? If we had a sum of logarithms, it would be the logarithm of the product. Okay? All right, so the question then, all of that was just to say that we can use pressure instead of concentrations. So the question says, if we begin with an initial pressure of blah, what is the pressure after 65 seconds? So you're going to simply go to your integrated rate law. Natural log of P, pressure, equals equals
Opposite.
negative KT plus the natural log of the original pressure. So it's the same question that we did just a minute ago, isn't it? The natural log of P equals negative 4.5 times 10 to the minus 2 per seconds times 65 seconds plus the natural log of 375 torr. So my answer is going to come out in torr, right? Pick up your calculator and evaluate all the stuff on the right-hand side. Did you get 3.00?
Yes.
Thank you, Mr. Richardson. You're doing something wrong, okay? So find out what you're doing wrong and fix it, okay? So natural log of P equals that. So what do I write now? P will equal E to the power of 3. 20. So second function, natural log to the power of 3, 20.1 torr. Okay? Part B, at what time will the pressure drop to 1/10 of its original value? At what time will the pressure drop to 1/10 of its original value? Let's solve this in two ways. There's sort of what I think for most of you is the obvious way. Start with the integrated rate law. Why are we using that integrated rate law, by the way?
This is the first order.
It was a first order process, right? And what do we know? What was P0? Do we know that? P0 was 375. So we know that. Do we know the rate constant? Yes. We're looking for how long will it take. So we're looking for T this time. That's the question mark. Do we know how much is there at the end? It said 1/10 is left, didn't it? So this P at the end would be 1/10 of 375. That's what I think most people would intuitively do. So do that and plug the numbers in, and then I'll show you a method of doing it a little bit different. So the natural log of 37.5 equals negative 4.5 times 10 to the minus 2 seconds to the minus 1 times t plus the natural log of 375. Okay, this question's easier to solve. You don't have to do any inverse logarithms. You don't have to do any e to the power of. So t will equal the natural log of 37.5 minus the natural log of 375, all divided by negative 4.5 times 10 to the minus 2. And because the units for k are in per seconds, this time is going to come out as seconds. Eugene, does that make sense to you? Whether, do you understand just from, if you don't understand where the original equation came from, can you accept that that's the integrated rate law for first order process? This question said it followed a first order kinetics, so we start with that equation. From there, the question gave us the rate constant. It gave us the initial pressure, 375 torr, and it says how long will it take to decrease to 1/10 of its starting value. So 1/10 of 375 is 37.5, so that's my p at time t. So now I've put those numbers in, and I'm looking for t. How long will it take? Okay. What's the answer to this? 51.2 seconds. Okay. Folks, we did not have to be told in this question what the starting concentration was. We did not have to be told the starting pressure. We could have simply been asked, how long will it take for a sample of SO2Cl2 to decrease to 1/10 of its starting amount? Do you understand what I'm saying? Why? Why do we not need to know the initial amount? The fact is, we could use anything. We could use anything for the starting amount, and then use 1/10 of that as the amount of time t. What would be the logical amount to use? 1. Why would 1 be a nice number to use? Let's do that. So the natural log, if we're going to say that the original pressure was 1, then how much is left? 1/10 is 0.1 equals negative k t plus the natural log of 1. What is the natural log of 1? What is the natural log of 1? 0. Because e to the power of what gives you 1? 0. E to the power of 0 is 1. That's why using 1 as the starting number is a very nice thing to do. Instead of saying 1/10, a common thing to do is to give you a percent. How long will it take to have 12% remaining? Okay? Same thing. Let the initial be 1, 12% remaining. This will be 0.12. Sometimes the wording is a little bit trickier. How long will it take for 90% to decompose? Oh, if 90% has decomposed, then 10% is remaining. 0.1 and 1. Do you follow? All right. Solve this, and what do you get? It should be the same thing. Can someone explain why it works? Why doesn't it matter what you started with? Why is it just as long as it's the 1/10? Max?
Just the rate.
No. Sabi?
Take 37.5 and 75 and divide that and reduce that fraction. It'll give you 1/10, and that can be multiplied to form any.
Exactly. So if I take the p, if I do that same trick we did on the previous slide, don't I get to this? Natural log of p over p0 equals negative kt, right? So whether you put 37.5 over 375, or 1 out of 10, or 0.1 over 1, it's the same ratio, it's the same fraction. Do you follow that? That's the mathematical justification for what we're doing here. So you should be able to get 51.2 seconds even with this. You don't need to know the starting amount. All you need to know is a fraction or a percent that decomposed. Okay? All right, you got about 8 minutes left. Why don't you try, did we finish that question? At what time? Yeah, we just did that. Number 40. Why don't you try number 40 and we'll finish with that today.